Welcome to Ask and Learn.
We're asked to show that there is no finite-state automaton that recognizes the set of bit strings containing an equal number of zeros and ones. To prove this statement, we'll prove it by contradiction. So we'll assume that a finite-state automaton M accepts the set of bit strings that contain an equal number of zeros and ones. Now let's assume, since it is a finite automaton, that M has n states. And consider the string 0 to the n plus 1, 1 to the n plus 1. So this is n plus 1 zeros followed by n plus 1 ones. Now, we know that the input 0 to the n plus 1 contains more inputs than states. Therefore, by the pigeonhole principle, it follows that there is an input there is a state that is going to be visited at least twice. So for pigeonhole principle, we have that the boxes are the states and the inputs are the pigeons, the objects. Now, this implies that n is going to end up in the same state with the input 0 n plus 1, 1 n plus 1, as with some input 0 to the n plus k plus 1, 1 to the n plus 1. Same state for 0 to the n plus 1, 1 to the n plus 1 as 0 to the n plus k plus 1, 1 to the n plus 1. Now, m accepts 0 to the m plus 1, 1 to the m plus 1, so it follows that m also has to accept 0 to the n plus k plus 1, 1 to the n plus 1. The reason m accepts 0 to the n plus 1, 1 to the n plus 1, by the way, is because there's the same number of zeros and ones, obviously. But it follows that 0 to the n plus k plus 1, 1 to the n plus 1 does not have the same number of zeros and ones, because k must be greater than or equal to 1. This is a contradiction. This means that it follows that m cannot have a finite number of states, but then it follows that m cannot be a finite state automaton, which is another contradiction. And so overall, we have found that such a machine does not exist.